Imagine that the length of a toilet roll represents the age of the Earth. Let's use it to unravel geological time. All 280 sheets of it. That was 4.6 billion years of Earth history. And this last sheet is about 16.5 million years. So where does humanity fall on this time scale? It barely spans the last perforations on the roll.
Well, Chris has shown us that it's not much use looking at the human history to get evidence for the age of the Earth. Our books, our bones, just simply don't extend far enough back into time for that to help us. But nonetheless, we've got to work with what we have in the present. In a place like this, where sand is actually being turned into rocks at the present time, and on the most enormous of scales, this is where we start. We have to use what we see at the present time to give us clues into what went on in the past. So what is going on in the present day? Well, every time there's a storm, wind blows sand from the bay here towards the land, and it makes these really fine layers. And I want to prove to you that those layers have to be older than these. And I've got a demonstration to do it. Fine glass jar. Now I'm going to pour in some sand. And on top of that, I'm going to pour in some pebbles. The two layers record two events. I poured in the sand, I poured in the pebbles. And it's pretty unthinkable, isn't it, that I could have got the sand in underneath the pebbles by doing it second. The sand had to go in first. And this establishes one of the fundamental tenets of geology. And that's the principle of superposition. And that says that under normal circumstances, the bed above is younger than the bed below. So when we look at layers of rocks, from top to bottom, we're reading back through the pages of Earth history. But so what? The beds at the bottom, are they 1,000 years old? 1,000,000 years old? 1,000 million years old? We don't know. But there are ways we can find out. We've come back to Morecambe Bay to look at the present time. And there's a nice cross-section down here which helps us understand it. Mostly sand, as you can see, the layers of sand that have blown in from the bay. And at the top the grass has grown. But here there's a rather surprising feature. The gravel in the middle of the sand. Now where's that come from? Well, the answer is it's part of the hardcore for this road. It's been put there by humans when they made the road. And we don't know when that was, or at least I don't know when it was, perhaps between the wars. But it gives us an absolute marker for how old these sands are. They must be older than that time between the wars. They're perhaps 70 or 80 years old or older. These must be younger. And of course the grass is younger still. That's the sort of evidence we need in the rock record. There's another point here too, and that's that whilst the sand blew in, perhaps over years, and the grass might have taken a couple of years to colonise, the gravel was put down by the cartload. That probably took just Monday to deposit. So that thickness was deposited very much more quickly than that thickness. Got some coins here, and I'm going to give you a history lesson of Britain in the last 2,000 years. Okay, off we go. First one is a Roman coin. I can see Caesar's head here. Second one, George III. Third one's got Queen Victoria, and the date is 1900, it's a penny. Fourth one's a half crown, comes from George the Fifth. Another half crown dated 1948. And last, a 10 pence coin, Queen Elizabeth's reign, 1990. So that's it then, that's the history of Britain in the last 2,000 years. Now you and I know that there's an awful lot missing there. There's nothing about Alfred and the cakes, there's nothing about the Fire of London, there's nothing about the First and Second World War and so on. But the great advantage of these coins in a succession like that is that each one is a very good indication of the time it was made. 1948, for example. Very clear indication. Just because you've got some bits of the record, it doesn't mean you've got the complete record. Now here's nature's coinage. They're fossils. I can see fossil colonies. I can see the spiral shell of a snail. And here a coral. These collections of fossils, called assemblages, are important because they characterize rocks. Now, life on Earth has evolved, much as coinage evolves over time. So I can use these particular fossils taken together to tell me what age this rock is. The fossils represent Carboniferous times, so these limestones must be Carboniferous limestones.
The discovery that different successions of assemblages of fossils could be recognised in different parts of England was made by William Smith almost 200 years ago. He was a surveyor and engineer involved in the construction of canals all over the country, so he had plenty of opportunity to see fresh exposures of rocks and collect fossils from them. And this enabled him to come up with the idea that different strata, as he called them, contain different assemblages of fossils. This is the oldest of the three examples of the illustrations of Smith's fossil assemblages. Each one has a different background colour to match the geological rock formations that Smith recognised. And not surprisingly, this one has a white background to match the matrix of this chalk bivalve fossil. The title of these sets of plates is Strata Identified by Organised Fossils. And this encapsulates Smith's recognition that a clear succession of rocks can be identified in different parts of England. And on top of that, that each of the units within that succession, his strata, is characterised by a distinct assemblage of fossils. And later he came to realise that each of these strata was associated with a discrete period of geological time. Well, to illustrate this idea, let's have a look at this demonstration. Let's suppose that these two lines of trays represent collections that Smith made at two locations in England. Using the law of superposition, we can assume that these trays at the base are the oldest, and so the collections get younger as we go in that direction. Let's see how these assemblages match up. In this tray, there are the remains of trilobites, and there's trilobites over here, so we can correlate these two. In the next one, there are shales with the remains of planktonic graptolites, and the same in the other tray. So they match up. And in the next tray, we've limestones with brachiopods, corals and crinoids, but something completely different in the other tray. A red sandstone, no fossils at all, so we can't correlate the two. But the tray above the red sandstone also contains brachiopods, corals and crinoids, so there's our correlation. So the sandstone is missing in this succession. And then the other two trays match up nicely, ammonites and belemnites in both. So there's our correlation line. And then finally at the top, remains of fossil mammals very similar to those living today. So these strata were probably only deposited a few 100,000 years ago, and there we can correlate them. So using this idea of correlating strata using fossils and his knowledge of the distribution of rocks throughout England, Smith published a wonderful geological map of the country in 1815. This map represents a milestone in the history of the geological sciences. It's one of the foundations of modern stratigraphy, the study of stratified rocks, how we can correlate them, and how we can use them to work out past events in the history of the Earth. Smith showed the distribution of his strata on the map by using watercolour washes. For instance, the chalk is shown in green, and a much heavier wash is used to show the base of the unit. And the same style is used for all the strata. Well, as well as recording his observations on the distribution of strata in 2 dimensions on this map, Smith also thought in the 3rd dimension. He drew a cross-section from London to Oxford to Worcester. The section extends northwestwards beyond Worcester into Snowdonia. To the northwest of Worcester, the simple southeastward inclination or dip of the strata that Smith shows is a gross oversimplification of what we know about the geology today. But to the southeast of the town, the section is remarkably accurate. It shows the English scarplands. Smith described these as being like slices of bread and butter arranged on a plate. The key to the map is a rudimentary stratigraphic column with the strata arranged in order, with the oldest at the base and the youngest at the top. Several of these names still appear on modern geological survey maps, which even use some of the same colours. We've seen how William Smith used the principles of superposition and faunal succession to work out a stratigraphic column for England. By about the middle of the 19th century, others had built on William Smith's ideas and defined the major geological periods: Carboniferous, Permian, Trias, Jurassic, and so on. And this work has continued. So today we can actually define quite small divisions. So using the range through the geological record of ammonites such as this, in other words, where they appear and where they disappear, it's possible to produce a very refined stratigraphic division of a particular rock sequence. There are 75 ammonite zones defined on ammonite species such as this in the British Jurassic. So that means that each ammonite zone lasted probably for about 1 million years on average. Now, once we've got this refined kind of record, we've realised that in places there are significant gaps in the stratigraphic record.
It's been said that the history of rocks is like the history of war. Vast periods of boredom interspersed with short episodes of terror. Actually, in the rock, most of the time is not in the body of the rock itself, but in the gaps between them. Now let's have a look at this little bit in here. We've got, it's all grey rock. This little bit is a lighter greeny grey, happens to be a bit sandier. That bit is a bit finer, a bit muddier. There's a sharp gap in here. Now, how might those have formed? Well, I'll show you. I'm going to make some rocks here in the back garden, and I want you to concentrate as I do it on how long each event takes. They're going to be a bit different from the ones we've just seen. Some wet sand. Some water. Now I'm going to shake it up. Now start watching. In just a few seconds, the sand has settled out. And I'm sure you can see a layer of sand forming at the bottom there. If we let enough time pass, the muddy bit is going to settle out as well. Now the mud is starting to settle out, but it's going to take several days, perhaps a week, for the water to clear. Nonetheless, we're forming a layer of mud on top of the sand. Now, event number 2. I'm going to add some more sand. I asked you to think about how long each of these events took. Now the two sands, the bottom one and the top one, settled out in seconds. The very thin muddy layer in the middle took much longer, days to settle. But the real time is between the two pourings of the sands. I could have put the second sand in days, weeks, even years later for all we know. And it's just the same in rocks. When we look at rocks, there is much more time in the boundary between two rock units than there ever is in the actual rocks themselves. So in layered rocks like these limestones, there's far more time represented by the boundary here than there ever is in the limestone underneath or the limestone up above. There are some special places where the immensity of geological time becomes clear. And this is arguably the most special of those special places. It's Siccar Point on the south coast of the Firth of Forth in Scotland. And it's here where the concept of an unconformity was first discussed and described. What is an unconformity? Well, it's a junction between two groups of rocks that are completely different in character and age. Let's work our way through this one now. The older rocks at this junction are these. They're grey rocks that were deposited deep in an ocean, and they've been tilted now so that the originally horizontal layers are standing up on end. And here they meet the younger group of rocks. The younger groups of rocks are red, much sandier, slightly tilted, and the junction between the two couldn't be clearer. And there are fragments of those older rocks up here within the beds of the younger ones. And why is Siccar so special? Because it's here that unconformities were discovered by James Hutton at the end of the 18th century. Now, Hutton was a fantastic scientist. He was the father of modern geology. He did an Einstein on the subject. He solved a problem before anybody else knew there was a problem there. And he came here with a group of friends to show them the immensity of what he'd discovered. And the account they wrote of the visit was electric. And I want to read part of it to you now. We made for a high rocky point or headland, the Siccar. On landing at this point, we found that we actually trode on the primeval rock. It is here a micaceous schistous in beds nearly vertical, highly indurated and stretching from southeast to northwest. The surface of this rock runs with a moderate ascent from the level of low water at which we'd landed to that of high water, where the schistous has a thin covering of red horizontal sandstone laid over it. This sandstone, a few yards further back, rises into a very high perpendicular cliff. Here, therefore, the immediate contact of the two rocks is not only visible, but is curiously dissected and laid open by the action of the waves. The rugged tops of the schistous are seen penetrating into the horizontal beds of sandstone, and the lowest of these last form a breccia containing fragments of schistous, some round and others angular. Dr. Hutton was highly pleased. On those of us who saw these phenomena for the first time, the impression made will not easily be forgotten. We felt ourselves necessarily carried back to the time when the schistous on which we stood was yet at the bottom of the sea, standing upright in vertical beds. And the sandstone was only beginning to be deposited. An epoch even more remote presented itself, when the most ancient of these rocks lay at the bottom of the sea and was not yet disturbed. The mind seemed to go giddy, looking so far into the abyss of time. So far, the rocks we've looked at have all been layered sedimentary rocks, but in many ways igneous rocks are better timekeepers because they represent moments in the geological time that they've been intruded. Now, this is a piece of Shap granite, beloved of geologists, and it comes from this quarry up here in Cumbria. You can see that it's made up of lots of interlocking crystals. If only we knew when these crystals formed. Well, I bet you're pretty frustrated that after all this, we've not once mentioned a date, an absolute age of rocks. It's all been relative this and relative that. And so were geologists for many decades, until we discovered this. This is a beta counter. And it measures radiation, and there's radiation all around us coming from space. Rocks are a little more radioactive. And when we discovered they were radioactive, we were able to measure the rate at which it decayed from this sort of value towards the background of this, and therefore find out how long it was since the rock crystallized. And in knowing that, we were at last able to find out the age of rocks. And this one, from Shap, is 395 million years old. Happy birthday, rock!
Mass spectrometers like this one can be used to measure incredibly small amounts of radioactive isotopes present in crystals, even single crystals. So this enables us to date the age of cooling of an igneous rock, the cooling age of a lava, or even the age of an ash fall. It's even possible sometimes to determine the age of minerals that are formed in sedimentary rocks. So this information enables us to put an absolute age on the succession of rocks that William Smith worked out 200 years ago. Even more than that, we can solve the ultimate question: how old is the Earth? Radiometric dating of meteorites, which consist of material that failed to aggregate into planets, gives the age of that event as around 4,600 million years ago. The oldest rocks which contain many clearly identifiable fossils are found in South Africa. These white and grey banded rocks are cherts, rocks composed of a variety of silica. Radiometric dating of igneous rocks associated with them indicates that they are around 3,500 million years old. These are the fossils found within the cherts. They are bacteria. They show that life must have begun on the Earth by that time. The chemical signatures of life, that is, organic compounds clearly derived from living matter, can be found in even older rocks, which date to around 3,800 million years ago. Radiometric dating enables us to give an age to many important events in the Earth's history and chart stages in the evolution of life. Sometimes we can even date the rock in which species make their first appearance and when they become extinct. So radiometric dating is a very important geological tool, whether used to date material incorporated into rocks millions or even billions of years ago, or material deposited on the Earth only a few thousands of years ago, where the geological and archaeological records meet.